There is a handgun that was designed in 1911, over a century ago, using technology that predates computers, advanced metallurgy, or modern manufacturing, built with tools that would be considered primitive today, sold to the military for $15 per unit. That gun is still in service, still being manufactured, still trusted by soldiers, police officers, and civilians around the world. Over 2.5 million were made for military use alone. Millions more for civilian market. And the ones built in 1911, if properly maintained, still function perfectly today. This is not normal. Most mechanical devices are obsolete within a decade. Guns designed in the same era are museum pieces. Technology moves forward. Materials improve. Designs evolve. Yesterday's cutting edge becomes today's antique. That is the pattern. That is how progress works, except for the M1911, designed by John Moses Browning, adopted by the United States military in 1911. Served through 2 world wars, Korea, Vietnam, and countless smaller conflicts, officially replaced in 1985. Except it was not really replaced. Many units kept using it. Special Operations Forces never stopped. And over a century after its introduction, new versions are still being built and sold. Why? What makes this gun different? What engineering decisions, what design choices, what accidents of genius created a weapon that refuses to become obsolete? The answer reveals principles of engineering that transcend firearms, lessons about simplicity, reliability, and functional design that apply to any technology, any tool, any system that needs to work under pressure for decades without failure. This is not a story about guns. This is a story about engineering excellence, about how to build something that lasts, about the difference between complexity and sophistication, about why sometimes the best solution is the simple one, about how $15 in brilliant design can create something worth infinitely more. The year was 1906. The United States military had a problem. Their standard issue sidearm, the Colt revolver in .38 caliber, was inadequate. This had been demonstrated conclusively during the Philippine-American War. American soldiers had shot enemy combatants multiple times center mass with the .38 caliber revolver. The combatants had continued fighting, had killed American soldiers, had proven that the .38 caliber round lacked stopping power. The military needed a new pistol, larger caliber, more stopping power, reliable under field conditions, and they needed it to be manufacturable at scale, affordable, easy to maintain, no delicate mechanisms that would fail in mud or sand or rain. This was a tall order. But the military's requirements were clear. They issued a challenge to firearms manufacturers: design a pistol that meets these specifications, submit it for testing. The military would conduct extensive trials. The winning design would receive a massive contract. The loser would get nothing. John Moses Browning was already famous by 1906. He had designed the Winchester Model 1873, the Model 1892, the Auto 5 shotgun, and dozens of other firearms. He was considered perhaps the greatest firearms designer who ever lived. When the military announced their pistol trials, Browning was the obvious choice to compete, but Browning had advantages beyond his reputation. He understood something fundamental about mechanical design, something that many engineers even today struggle to grasp. Simplicity is not the same as crudeness. A simple mechanism can be sophisticated if every component serves multiple purposes, if every part is exactly the shape and size it needs to be and nothing more, if the design eliminates everything unnecessary and keeps only what is essential. This philosophy would define the M1911. Every part of the pistol served a purpose. Nothing was decorative, nothing was redundant. The design was stripped down to functional essence, and in that essence, Browning found elegance. The heart of the M1911 is its operating system. When you fire the pistol, several things must happen in precise sequence. The bullet must leave the barrel. The spent cartridge case must be ejected. A new round must be loaded from the magazine. The hammer must be cocked for the next shot. All of this must happen reliably, quickly, and without requiring any action from the shooter beyond pulling the trigger again. Browning solved this with a mechanism called short recoil operation. When the gun fires, the barrel and slide are locked together. They recoil backward together for a short distance. Then, the barrel tilts slightly downward, unlocking from the slide. The slide continues rearward alone, ejecting the spent case and cocking the hammer. A spring then drives the slide forward, stripping a new round from the magazine and pushing it into the chamber. The barrel and slide lock together again, ready for the next shot. This all happens in a fraction of a second, faster than human perception. The shooter pulls the trigger. The gun fires. The gun is ready to fire again. No conscious thought required. No manual manipulation. Just pull the trigger. The mechanism does everything else. The genius is in how few parts are needed. Barrel, slide, frame, recoil spring, magazine, hammer, trigger, disconnector, sear, grip safety, thumb safety. Total parts count is approximately 58, depending on how you count small pins and springs. This is remarkably few for a semi-automatic pistol. Fewer parts means fewer things that can break, fewer things that need to be manufactured precisely, fewer things that can go out of tolerance. Simplicity creates reliability, but simplicity alone is not enough. The parts must be designed correctly. This is where Browning's genius truly shows. Every component of the M1911 is shaped to be strong where strength is needed and just adequate everywhere else. Nothing is overbuilt. Nothing is underbuilt. Everything is exactly right. Consider the barrel. It must contain the pressure of the cartridge firing, pressures that peak around 21,000 pounds per square inch. The barrel must not rupture, must not deform, must maintain accuracy through thousands of firings, but it also must not be so heavy that it unbalances the gun, must not be so thick that it requires an enormous slide to cover it. Browning's barrel is thick at the chamber, where pressure is highest, thinner toward the muzzle, where pressure has dropped. The rifling is cut precisely. 4 grooves, right-hand twist, enough to stabilize the bullet without excessive friction. The chamber is tapered to facilitate extraction. The feed ramp is polished smooth. Every dimension serves a purpose. The slide is even more impressive. It must be strong enough to contain the recoiling barrel. It must be heavy enough to slow the recoil spring appropriately. Must have cuts for the ejection port that do not compromise structural integrity. Must have serrations for gripping that do not create stress concentration points. Must have rails that ride smoothly on the frame for decades of use. The slide is essentially a rectangular block of steel with strategic material removed. But where that material is removed matters immensely. Remove too much and the slide cracks. Leave too much and it is unnecessarily heavy. Browning found the balance. The ejection port is sized to reliably clear spent cases but no larger. The serrations are angled to provide grip without catching on clothing. The rails are hardened but not brittle. Every detail optimized. The frame is where multiple design challenges converge. It must house the trigger mechanism, must provide a grip for the shooter, must have a magazine well that feeds reliably, must mount the slide rails, must contain the recoil spring, Must do all this while being strong enough to handle recoil forces, but light enough to be practical. Browning's frame is a masterwork of structural efficiency. The grip angle is 108 degrees, not 90 degrees vertical, not 120 degrees like some competition guns, exactly 108. This angle naturally aligns the gun with the shooter's arm, points naturally, reduces muzzle rise during firing. Browning tested multiple angles, 108 was optimal. The magazine well is flared slightly, not visible to casual inspection. But the flare guides magazines during insertion, reduces fumbling during reloads, a detail that seems minor until you are reloading under stress. Then that small flare becomes important. The trigger mechanism is brilliantly simple, single action only. The hammer must be cocked before the gun will fire. This was intentional. Double action mechanisms, where pulling the trigger both cocks and releases the hammer, are more complex, more parts, more things to break, more difficult trigger. Pull. Browning chose simplicity, single action. Cock the hammer manually or let the slide do it during firing. Clean, simple, reliable. But a single action trigger creates a safety problem. If the hammer is cocked and the trigger is light, the gun could fire if dropped. Unacceptable. Military specification required multiple safety mechanisms. The gun must not fire if dropped. Must not fire unless the shooter deliberately pulls the trigger with the safety disengaged. Browning solved this with two safeties that are nearly invisible in operation. The thumb safety on the left side of the frame is obvious. Flip it up. The gun cannot fire. Flip it down. The gun is ready. Simple, positive, easy to operate even with gloves or under stress. The second safety is the grip safety, a lever at the back of the grip. When you hold the gun properly, your hand depresses the grip safety. The gun can fire. If you are not holding the gun, the grip safety is not depressed. The trigger is mechanically disconnected. The gun cannot fire, even if the thumb safety is off and the trigger is pulled. These two safeties work together seamlessly. Hold the gun, disengage thumb safety, pull trigger. The gun fires. Drop the gun or hand it to someone who grabs it incorrectly, and the grip safety prevents firing. It is foolproof. It requires no thought once you are trained. Your natural grip depresses the grip safety automatically. This is sophisticated simplicity. Two mechanical safeties that add minimal parts count, but provide maximum safety. Both are passive. Both require deliberate action to overcome. Both are nearly impossible to defeat accidentally, and neither interferes with normal operation. The magazine is another masterpiece. It holds 7 rounds of 45 ACP ammunition. The follower is a simple stamped metal part. The spring is music wire wound with precise tension. The feed lips are shaped to present cartridges at the exact angle the slide needs to strip them reliably. The magazine body is steel, welded at the base, dimpled to reduce friction. Total parts in the magazine: 4. Body, follower, spring, base plate. Yet this simple assembly must feed reliably through thousands of cycles, must not dent, must not lose spring tension, must not allow dirt to interfere with feeding, and it works. Magazines designed in 1911 still function today if not abused. The cartridge itself deserves mention. The 45 ACP automatic Colt pistol was designed alongside the gun. Browning and Colt worked together to create a cartridge that would meet military requirements: large caliber, sufficient stopping power, reliable feeding, moderate recoil, acceptable barrel life. The result is a rimless, straight-walled cartridge that is nearly impossible to feed incorrectly. The straight walls prevent case setback during feeding. The rimless design allows reliable extraction. The large diameter, provides substantial stopping power. The relatively low pressure extends barrel to life. The cartridge and gun were designed together, each optimized for the other. This is systems engineering before the term existed. Browning did not just design a gun, he designed a complete system. Gun, cartridge, magazine, all optimized to work together, all designed with the same philosophy. Simple, reliable, functional, nothing unnecessary, everything essential. The metallurgy deserves examination. Remember, this was 1911. Modern alloy steels did not exist. Advanced heat treatment was limited. Manufacturing tolerances were looser than today. Yet the M1911 was designed to last. Browning specified carbon steel for most parts, not stainless. Carbon steel can rust, but it is stronger and easier to heat treat to precise hardness. The slide and barrel required hardness to resist wear but could not be brittle. Browning specified case hardening. Heat the surface to high temperature, introduce carbon, then quench. The surface becomes hard. The core remains tough. The part resists wear but does not crack. The frame could be slightly softer. It did not experience the same wear as the slide. Browning specified a lower carbon content, easier to machine, less likely to crack. Still plenty strong for the loads involved. Every part was specified for its role. Not one universal material for everything. Tailored metallurgy for each component. Manufacturing was another challenge. The military wanted thousands of pistols, eventually millions. They needed to be made by multiple manufacturers. Parts needed to be interchangeable. A slide from one manufacturer should fit a frame from another. This was ambitious for 1911. Browning designed for manufacturability. Most parts are simple shapes, rectangles, cylinders, angles that are easy to machine. No complex curves requiring special tooling. The most complex parts, like the hammer and sear, are small, can be forged then finished, economical to produce. The tolerances are looser than you might expect. The slide to frame fit has noticeable play, intentional. Tight tolerances require precise machining, expensive, and tight fits are vulnerable to dirt. A loose slide rattles slightly but keeps functioning even when full of sand. Browning chose function over precision fit. The gun is reliable, not jewel-like. Exactly what military service requires. Field stripping is brilliantly simple. Remove magazine, lock slide back, rotate barrel bushing, remove recoil spring plug, release slide, pull slide slightly back, lift rear of slide, slide comes off frame, flip barrel link, remove barrel, 5 major assemblies, slide, frame, barrel, recoil spring, barrel bushing, no tools required. A soldier can strip the gun, clean it, and reassemble it in minutes, even in dark, even with cold hands, even under stress. This ease of maintenance is critical. Complex guns require armorer-level maintenance. Soldiers in the field cannot service them. The M1911 can be maintained by anyone with minimal training. Clean it, lubricate it, reassemble it. It will work. This made it practical for mass military use. The testing process was brutal. The military trials in 1907 tested multiple designs, 6,000 rounds minimum through each pistol, fired continuously until too hot to hold, dunked in water, fired again, covered in sand, fired, dropped repeatedly, fired, exposed to rust, fired. The trials were designed to break the guns, to find their limits, to prove which design could survive abuse. Browning's design passed everything, not just barely, easily. The M1911 fired 6,000 rounds with only one malfunction, a broken firing pin spring replaced in minutes. The gun continued firing. By the end of the trials, it was clear. Browning's design was superior. The military adopted it. Production began. But adoption was just the beginning. The real test was decades of military service, millions of pistols, billions of rounds fired, every environment imaginable: Arctic cold, desert heat, jungle humidity, ocean salt spray, mud, sand, dust, blood. The M1901 experienced it all. And it kept working, not perfectly. No mechanical device is perfect, but reliably. When soldiers needed their sidearm, it functioned. Stories from World War I describe pistols pulled from mud and fired without cleaning. Stories from World War II describe pistols that had not been cleaned in months still functioning. Stories from Vietnam describe pistols that had fired tens of thousands of rounds still operating. This reliability built a reputation. Soldiers trusted the M1911. They knew it would work. That psychological factor is as important as the mechanical reliability. A weapon you trust is a weapon you will use effectively. A weapon you doubt creates hesitation. The M1911 eliminated doubt. The simplicity also meant it could be manufactured at enormous scale. During World War II, multiple manufacturers produced MY1911 pistols. Colt, of course, but also Remington Rand, Ithaca, Union Switch and Signal, and Singer Sewing Machine Company. Yes, Singer, famous for sewing machines. They built pistols during the war. The design was simple enough that even a company with no firearms experience could manufacture it successfully. Parts interchangeability was generally good. A Singer slide would fit a Colt frame, not perfectly. There might be more play, but it would work. This allowed battlefield repairs using parts from damaged guns, enormously practical for sustained combat operations. Lose your pistol? Here is another from the supply sergeant. It may be from a different manufacturer, but it works the same. Muscle memory transfers perfectly. Post-war, the MY911 continued evolving, not drastically. The basic design remained unchanged, but small improvements were made. Better sights, different grips, improved finishes. The core mechanism stayed the same because it worked. Changes were to accessories and ergonomics. The engineering perfection of the basic design was not touched. 1926, minor modifications were made. The trigger was shortened. The grip safety tang was lengthened. The mainspring housing was changed from flat to arched. The new variant was designated M1911-1. These were minor changes. The fundamental design was untouched. The changes made the gun fit more hands comfortably, made the trigger easier to reach for shooters with smaller hands. Practical improvements that did not compromise the core brilliance. The M1911 served through World War II, Korea, and Vietnam. Millions more were produced. The changes proved successful, but again, the core design remained. Barrel, slide, frame, recoil operated, 45 ACP, single action trigger, grip and thumb safeties. The formula established in 1911 still worked in 1969, still works today. In 1985, the military officially replaced the M1911A1 with the Beretta M9. 9mm, higher capacity, lighter recoil, double action trigger. The decision was controversial. Many soldiers preferred the M1911A1, preferred the stopping power, preferred the familiarity, preferred the reliability they had come to trust. Special operations units were allowed to continue using the M1911A1. Marine Special Operations, Army Special Forces, they kept their pistols, and civilian companies began producing modern variants, improved metallurgy, modern finishes, better sights, accessory rails, but the core design, unchanged, over a century old, still trusted, still preferred by many over modern alternatives. Why? Why does a design from 1911 remain relevant when smartphones become obsolete in 2 years? when cars are redesigned every generation, when technology advances relentlessly? What makes the M1911 timeless? The answer is that Browning solved the problem perfectly. Not adequately, not sufficiently, perfectly. He identified the essential requirements: reliable firing, adequate accuracy, sufficient stopping power, ease of maintenance, manufacturability, and he created a solution that optimally balanced all these requirements. There was no fat to trim, no complexity to remove, no obvious improvement to make. This is extremely rare in engineering. Most designs are compromises, optimized for one factor at the expense of others, or designed with unnecessary complexity because the engineer was showing off, or designed to be cheap rather than functional, or designed without understanding the actual requirements. Most designs can be improved. The M1901 cannot be meaningfully improved without fundamental redesign. You can add features, rails for lights, better sights, different grips. But the core mechanism, already optimal. Changing it makes it different, not better. This is the mark of genius, solving a problem so well that the solution endures for a century. Consider what has changed since 1911, 2 world wars, the atomic age, the computer revolution, the internet, smartphones, advanced materials, computer, aided design, finite element analysis. We can simulate stress and failure modes with incredible precision. We can manufacture to tolerances Browning could only dream of. We can use materials that did not exist in his time. And yet, modern pistol manufacturers cannot design something that makes the M1911 obsolete. They can design pistols with higher capacity, with lighter recoil, with different features, but they cannot design a pistol that is more reliable, more durable, more trusted. The M1911 remains the standard by which other pistols are judged, over a century after its introduction. This should be humbling for modern engineers. We have tools Browning never imagined. We have knowledge he did not possess. We have resources he could not access. And yet, we cannot improve on his core design. He got it right. First time, with pencil and paper and intuition and genius. There are lessons here that transcend firearms, lessons about engineering philosophy, about design, about what makes technology endure. First lesson: simplicity is sophistication. The M1911 works because it is simple, fewer parts, fewer failure modes, easier to maintain. But the simplicity is not crude, it is sophisticated. Every part serves multiple purposes. Every dimension is optimized. Nothing is arbitrary. This is the difference between simple and simplistic. Simple is elegant. Simplistic is crude. Second lesson: design for the use case, not the ideal case. Browning did not design a pistol for range use. He designed it for combat, for soldiers in mud and blood and chaos, for users who might not clean it for weeks, for conditions where reliability matters more than perfection. He accepted looser tolerances because tight tolerances fail when dirt gets in. He accepted visible wear because worn parts that function are better than pristine parts that break. He designed for reality, not theory. Third lesson: optimize the system, not just the components. The M1911 works because gun, cartridge, and magazine were designed together, each optimized for the others. Many modern guns fail because components are designed in isolation. The magazine feeds poorly. The cartridge does not extract cleanly. The gun looks good on paper, but fails in practice. Browning understood systems thinking before it had a name. Fourth lesson: test ruthlessly. Do not trust calculations. Test the actual product under actual conditions. Then test it harder. Find the breaking point. Understand the failure modes. Fix them. Test again. The M1911 went through brutal testing. The testing found weaknesses. Those were fixed. The final product was proven through trial, not assumed to work, proven to work. Fifth lesson, do not add features unless they serve a clear purpose. The M1911 has two safeties because two are needed. It does not have three or four. It has a single action trigger because that is sufficient. It does not have double action because that adds complexity without meaningful benefit for military use. Every feature exists because it solves a problem. No features exist because they seemed like a good idea. This discipline creates functional design. These lessons apply to any engineering problem. Building software, designing bridges, creating medical devices, any system that must work reliably under stress over time. The principles are universal: simplicity, reality-based design, systems thinking, rigorous testing, functional purpose. Apply these and you create designs that endure. The M1911 is over a century old. New ones are being manufactured today, not as historical replicas, as functional tools, purchased by serious users who trust proven design over marketing hype. That is the ultimate validation. The market, when informed, chooses the M1911. Despite having countless modern alternatives, despite advanced materials and computer design, the market chooses Browning's century-old design. That $15 pistol from 1911 is worth far more than its original price. Not in collectible value, though original examples are valuable. In functional value, a new M1911 costs $600 to $2,000 depending on manufacturer and features. People pay that gladly because they are buying proven reliability. Buying a design that works, buying a century of trust. John Moses Browning died in 1926. He did not live to see his pistol serve through World War II, did not see it become iconic, did not see it endure into the 21st century. But his work lives on, not just the M1911. He designed over 80 firearms. Many are still produced today. The Browning Auto 5 shotgun, the Browning high-power pistol, the M2 Browning machine gun still in military service. His designs define firearms, but the M1911 is special. It is the purest expression of his philosophy. Simple, reliable, functional, nothing unnecessary, everything essential, optimized for purpose, tested ruthlessly, built to last, and lasting it has, through a century of use, through wars and conflicts, through billions of rounds fired, through the hands of millions of users. The design endures. This is what $15 and genius can create, not just a gun, a standard, a benchmark, a demonstration of engineering excellence that transcends its specific application. The M1911 teaches us how to build things that last, how to design for purpose, how to achieve sophistication through simplicity, how to create value that endures for generations. When you hold an M1911, you are holding history. You are holding proof that good design is timeless. You are holding evidence that sometimes the old way is the best way. Not because it is old, but because it is right. Browning got it right. The century since has confirmed it. The M1911 is not obsolete. It is validated again and again, year after year, decade after decade, century after century. That is the engineering secret, not a trick, not a shortcut, just principles, applied rigorously, tested thoroughly, refined relentlessly. The result is a design that does not age, does not become obsolete, does not need replacement, just works. Now, tomorrow, forever. $15 in 1911, priceless in value, timeless in design, perfect in execution. That is the M1911. That is engineering genius. That is what makes a gun last 100 years. The metallurgical choices Browning made deserve deeper examination because they reveal thinking that was decades ahead of his time. In 1911, steel metallurgy was understood but not optimized the way it is today. Different steel compositions were known, but the relationship between composition, heat treatment, and final properties was still being explored through trial and error. Browning understood intuitively what modern metallurgists prove through testing. Different parts experience different stresses. A slide experiences cyclic loading, repeated impacts as it reciprocates during firing. This causes fatigue. The material must resist crack propagation. Too hard and it becomes brittle. Cracks form and spread. Too soft and it deforms, loses dimensional accuracy. The slide needs a balance. Hard surface to resist wear. Tough core to resist cracking. The barrel experiences different stress, internal pressure from firing, heating and cooling cycles, friction from the bullet. The rifling must not erode quickly. The chamber must not stretch, but the barrel also must not crack. Browning specified a medium carbon steel, high enough carbon for hardness, low enough for toughness, then case hardened the chamber and rifling. The surface is very hard, resists erosion. The core is tougher, resists cracking from pressure spikes. This selective hardening requires understanding of stress distribution. The chamber experiences highest pressure, needs maximum hardness. The muzzle experiences lower pressure but higher friction from the bullet, needs moderate hardness. Browning did not have finite element analysis. He had experience and intuition. He knew where stress concentrated, specified treatment accordingly, got it right. The frame experiences yet different stress, not cyclic like the slide, not pressure like the barrel, mostly static loads, the weight of the slide, the recoil impulse transmitted through the slide rails, occasional impacts from dropping. The frame needs strength but not extreme hardness. Too hard and it becomes brittle. Will crack if dropped. Browning specified lower carbon steel, adequate strength, better toughness, appropriate for the application. This material selection is systems thinking, each part optimized for its role, not one universal material for everything. Modern pistols often use stainless steel for everything, easier manufacturing, better corrosion resistance, but inferior material properties for some applications. The M1911's carbon steel approach is metallurgically superior, requires more care to prevent rust, but provides better mechanical properties. The surface finish matters too. The M1911 was originally finished with a process called bluing. Controlled oxidation of the steel surface creates a thin layer of black iron oxide, provides minimal corrosion protection, but more importantly, reduces glare. A shiny pistol reflects light, gives away position. The blue-black finish is tactical, functional, not decorative. Later variants use different finishes: Parkerization during World War II, phosphate coating, better corrosion resistance, rougher texture, actually improved reliability in some ways. The rough surface held oil better, provided lubrication under adverse conditions. The aesthetic was industrial, purely functional, but effective. Modern M1911 variants use many different finishes: stainless steel, nickel plating, Cerakote, hard chrome. Each has advantages, but the original bluing and later Parkerization were optimized for military use: durable, practical, easy to apply, easy to touch up in the field. Another example of design for use case rather than ideal case. The ammunition deserves more attention too. The .45 ACP cartridge was revolutionary in 1911, not because of extreme power, but because of balance. Prior pistol cartridges were either low power or produced excessive recoil. The .45 ACP provided stopping power with manageable recoil. This required careful balancing of several factors. Bullet weight is 230 grains, heavy for a pistol. Provides momentum, transfers energy to target efficiently, but heavy bullets require more powder to achieve acceptable velocity. More powder means more recoil. The balance is careful. Just enough velocity for effectiveness, not so much that recoil becomes unmanageable. Velocity is approximately 830 feet per second from a 5-inch barrel. Subsonic. The bullet does not break the sound barrier, avoids the turbulence and accuracy problems associated with transonic flight, produces less noise, less muzzle blast, more pleasant to shoot, easier to train soldiers, subtle but important. Chamber pressure is moderate, 21,000 pounds per square inch peak, high enough for effective bullet performance, low enough for reasonable barrel life. Lower pressure means less wear. Barrels last longer. Reduced manufacturing cost over the lifetime of the military contract. Economic thinking embedded in technical decision. The cartridge case is straight-walled, simplifies feeding. Curved cases can catch on feed ramps, cause malfunctions. Straight cases feed smoothly. The rim is slightly narrower than the body, called rebated rim design. Allows reliable extraction without protruding rim that could cause feeding issues. Every dimension serves a purpose. The primer is standard large pistol. Easy to ignite, reliable, widely available. Does not require special manufacturing. Uses commercial components. Another example of practical design. Exotic components create supply chain problems. Standard components ensure availability. Browning thought about logistics, about supply chains, about sustainability, not just immediate performance. These decisions about the cartridge seem minor. They are not. The cartridge must function reliably, must be manufacturable at massive scale, must be affordable, must be effective, must be consistent lot to lot, must remain stable in storage for years. The 45 ACP meets all these requirements, has met them for over a century. Ammunition loaded in 1918, if stored properly, will still fire reliably today. That is remarkable engineering. The interaction between cartridge and chamber is critical. The chamber must be precisely sized, too tight and cases stick. Extraction failures, too loose and case heads can rupture. Gas leaks, dangerous. Browning specified chamber dimensions that provide reliable extraction while maintaining safety margins. The chamber is slightly tapered. Cases expand during firing. The taper allows easier extraction. Small detail, huge impact on reliability. The feed ramp geometry is equally critical. The ramp guides cartridges from magazine to chamber. The angle must be correct. Too steep and bullets nosedive, too shallow and they jam. The ramp surface must be smooth. Rough surfaces cause friction, feeding problems. The transition from ramp to chamber must be seamless. Any step causes jams. Browning specified a compound curve, matches the cartridge profile perfectly. Feeding is smooth and reliable. This attention to geometry is evident throughout the design. The extractor hook must grip the case rim firmly. Too loose and cases are not extracted. Too tight and the extractor breaks. The hook shape is carefully designed, provides reliable grip without excessive force. The extractor itself is spring-loaded, provides constant tension, compensates for wear, dimensional changes from heating. Brilliant, simple solution. The ejector is a fixed tab on the frame. As the slide moves rearward, the case hits the ejector, gets flipped out the ejection port. The timing must be precise. Too early and the case does not clear the port. Too late and the case hits the closing slide. Browning positioned the ejector exactly right. Cases eject reliably, clear the port, land several feet to the right, consistent, predictable, functional. These details are invisible to most users. The gun works, that is all they see. But the gun works because hundreds of small decisions were made correctly. Every angle, every clearance, every surface finish, every material choice, all optimized, all proven through testing, all refined to perfection. This is the accumulation of genius, not one brilliant insight, hundreds of correct decisions. The trigger mechanism deserves detailed examination. The trigger is the interface between shooter and gun. It must be safe, must be consistent, must provide good feel, must be reliable. These requirements are partially contradictory. Safety requires heavy pull weight, good feel requires light pull. Browning balanced these requirements brilliantly. The trigger pull on a properly tuned M199 weight is approximately 4 to 5 pounds, light enough for precise shooting, heavy enough for safety. The pull is single stage, no take-up, no creep. The trigger moves, resistance builds slightly, the sear releases, the hammer falls, clean break, resets positively, consistent pull to pull. This consistency is critical for accurate shooting. The mechanism is simple. Trigger pivots on a pin, pushes the sear. Sear releases the hammer. Hammer falls, strikes firing pin, gun fires. 3 moving parts in the trigger system: trigger, sear, hammer, plus springs, plus pins. Total parts count under 10. Minimal complexity, maximum reliability. Compare this to modern double-action triggers, dozens of parts, complex linkages, more to break, more to tune, more to go wrong. The grip safety adds complexity but minimal. It blocks the trigger unless depressed. Mechanical linkage is simple, reliable, does not interfere with function when properly held. This is elegant safety design. Automatic, passive, requires no thought, no extra action, just hold the gun normally. Safety is defeated automatically. Release the gun. Safety engages automatically. The thumb safety is equally elegant. Up for safe. Locks the sear directly. Hammer cannot fall. Down for fire. Sear is free. Positive clicks. You can feel the engagement. You can hear it. No ambiguity. The safety is either on or off. No in between. No partial engagement. Binary, clear, functional. These safeties work together to create layered defense against accidental discharge. For the gun to fire, you must hold it properly to depress the grip safety. You must disengage the thumb safety deliberately. You must pull the trigger with approximately 4 pounds of force. 3 independent requirements. All must be met. The probability of accidental discharge is extremely low, yet none of these safeties interfere with deliberate firing. Hold the gun, flip the safety, pull the trigger, fast, instinctive, reliable. This is sophisticated mechanical design. Multiple safeties that layer redundancy without creating complexity, that prevent accidents without hindering intentional use, that are passive and automatic rather than requiring conscious thought. Modern safety engineering teaches these principles. Browning applied them instinctively in 1911. The sights on the original M1911 were rudimentary. Small notch rear, small blade front, adequate for combat ranges, not precision instruments. This was intentional. Sights get damaged. Elaborate sights break. Simple sights are durable. For military use, durability trumps precision. The sights were good enough for their purpose. Hitting center mass at 25 yards, that is the requirement. Elaborate target sights would be wasted capability. Modern M1911 variants often have better sights, larger, more visible, sometimes with tritium inserts for low light. These improvements are valid for civilian and competition use. But for military use, the original simple sights were optimal. Another example of design for purpose, not overbuilding, not adding unnecessary features, just adequate performance with maximum durability. The magazines are often underappreciated. They seem simple, just a box with a spring. But the magazine is where feeding problems originate. Poor magazine design causes more malfunctions than any other factor. Browning's magazine design is brilliant in its simplicity and effectiveness. The feed lips are the critical feature. They control how cartridges are presented to the slide. The lips must hold cartridges at the correct angle, must release them at the correct time, must not deform under spring pressure, must not crack, must not corrode. Browning shaped the feed lips with compound curves. The shape provides strength and correct cartridge presentation simultaneously. Single feature serves multiple purposes. Elegant. The magazine spring is music wire, high carbon steel wire wound into a coil. It must provide adequate force to feed 7 rounds reliably, must not take permanent set, must not break, must fit in the limited space available. Browning specified wire diameter and coil count precisely. The spring works reliably for decades, can be compressed and released thousands of times without failure. Simple part, perfectly specified. The follower is stamped steel, shaped to match the internal magazine dimensions, dimpled to reduce friction. The shape provides rigidity despite thin material, prevents binding, allows smooth travel. The dimples trap oil, provide lubrication, reduce friction, prevent corrosion. Simple stamped part doing multiple jobs effectively. This is economical engineering. Minimal material, maximum function. The magazine body is welded steel, seam welded up the back. The weld is the weak point. If it fails, the magazine is junk. Browning specified adequate material thickness, proper welding technique. The welds hold. Magazines from 1918 still function today. 100-year-old welds, still intact. That is quality manufacturing enabled by good design. Proper material selection, appropriate processes, adequate margins. These details accumulate. Barrel works, slide works, frame works, trigger works, safeties work, magazine works, everything works, and everything works together. That is systems engineering, not just designing parts, designing the system, making sure all parts cooperate, making sure interactions are positive, making sure the whole is greater than the parts. Browning did this instinctively. Modern engineers use complex tools to achieve what he achieved with intuition and testing. The ultimate validation of the M1911's design is not technical analysis, it is usage. Millions of pistols, billions of rounds, century of service, under every conceivable condition, and the design persists, not because of marketing, not because of tradition, because it works. When lives depend on equipment, people choose what works. They have chosen the M1911 repeatedly, consistently, for over a century. That is the final lesson. Good design proves itself through use, through time, through stress. Theory is useful, analysis is important, but reality is the ultimate test. The M1911 passed, keeps passing, will pass for the foreseeable future. That $15 pistol has earned its place in history, not through hype, through proven reliability, through accumulation of correct decisions, through genius expressed in steel. John Moses Browning created something timeless. Not intentionally, he was solving a problem. Military needed a pistol, he designed one. But in solving that problem, he created a template, a standard, a demonstration of how to design mechanical systems that endure. The lessons extend far beyond firearms. Apply to any engineering discipline, any technology, any system that must work reliably under stress over time. simplicity, systems thinking, reality-based design, rigorous testing, functional purpose, material optimization, manufacturing consideration. These principles are universal, timeless. Apply them and you create designs that last, that work, that prove themselves through decades of use, that become standards against which everything else is measured. The M1911 is that standard, not perfect. No design is perfect, but optimal for its purpose. Proven through a century of use, validated by millions of users, trusted, reliable, enduring. That is what $15 and genius can create. That is the engineering secret, not a secret at all. Just excellence, applied rigorously, sustained over time, proven through reality. That is the M1911. That is timeless design.